Hello, welcome. Today we have daily as flip columns for maximum number of equal rows. So what it says that we have a binary matrix of size m into n, and we can choose any number of columns in a matrix and flip every cell. Flipping means making 1 to 0 and 0 to 1. It's basically like you have a whatever the content here, let's say matrix of ij, and you're XORing it to 1, so it flips every time. You can use this at making state dp whenever you're making like n into 2 and you have to write 1 0, just like XOR this to 1 every time, it will change the state. So this is like an extra information not related to this question, but just letting you know. So and it says you can always choose any number of columns in a matrix and flip every cell in that column. uh, Flipping means 1 to 0, 0 to 1, that is vice versa, and you have to return the maximum number of rows that have all values equal after some number of flips. So what we can see here, it's like uh, this is called the row and this is called the column of it. Even if we look at the example 0 1 1 0, right, at the example here, let's say we are picking this to flip or this to flip. We can always assume that we have one equal array, sorry, one equal row always, right? Because let's say every row is different, like this, every row is different, but we will still have one row as a maximum equal because it is equal to itself. So the answer would always be 1. So we have 1, right, as an always an answer. Now if, sorry, it is 1 1. So if we are flipping this, we can make it 1 0, and if we're flipping this, it can be 0 0. Or if we flip like one of these, like if we are flipping this here, we can make it 1 0 and 1. As we can see, out of every combination, we cannot make it equal. And what does equal actually means? Equal can be considered in three possible ways. Either they're exactly equal, sorry, exactly equal. That means all zeros, all ones, right? Or they're exactly opposite. Now what does this mean? Let's say 1 0 1 and 0 1 0. Would you say this is an equal? Yes, this is. Why? Because we can always flip this to make it equal to the next one. As you can see, this is these is the condition that we want to have. And if like I have to say that how, where the intuition lies or how we will start thinking, then we can always start by greedily flipping everything into what we want. And what we want here, we want to make it all alike. So let's say I have this one, right, 0 0 0 0 0 1 and 1 1 0. This is what we have, right? Now if we look at these both rows, are they equal or not? Let's check our both conditions. Are they exactly equal? No, because there are some zeros, there are some ones, there are some one, there are zero. But are they exactly opposite? Yes, because every zero has a complementing to 1, every 0 is complementing to 1, every 1 is complementing to 0. So if there are some operational present performed on this ones, they will be equal to these ones. So what we have to check is like either I am considering this or all zeros. So for that you can always check if the first element of an like a row is 1, flip everything, like make it 0, and make it 1. And same with this, like flip everything here, like you just flip every row to its complement. So the at the end of the day it will be accumulated together. So what I'm trying to say, it's not complex. It's like if we have 0 0 1, right, and 1 1 0, flip it to 1 1 0 and flip it to 0 0 1. Now as I can see, I can gather 2 from it, this matrix, like 2 0 0 1s and 2 1 1 zeros. Now if this would have been not here, still I would have an 1 as an equal one, like I would have 1 0 0 1 and 1 1 1. So the maximum would always be 1. But what I'm trying to say, if I'm trying to feed this, like it's not just the starting is 1 or starting is 0. I'm just saying just flip the bits, so that if they're exactly equal, like 1 1 1 1 1, there'll be 0 0 0 zeros, and this is always equal to 0. So this will be 1 1 1 and 1, and this one would be same. Or the case I'm trying to handle is 0 0 1, then if would be 0, then this would be 0 1 1 0 and 1 0 0 1. So this is also equal. So the every alike matrix would be like accumulated, alike vectors of matrix, like this row of the matrix will be accumulated, and we will have the maximum alike after storing in a like hash or something, because the constraint is 300. So we can use bit set or something, but using a vector is always good. We can always use a good vector. So the whole intention, the uh, approach of this problem lied in what are the equality means and how we can deduce after complementing it. So it was not a hard question, but it was very good medium, because you have to like observe on examples to know what's happening, and you can solve them by just reducing the problem. So let's, if we like, I have to further think of it that how even this is working. Just take 2 examples where you cannot make them equal, like make them 1 0. Now you cannot make them equal, because flipping this would be different and flipping this would be different. So this both are not same, because neither they are all zeros, all ones, or exactly opposite. So that's being said, uh, we can implement it very easily. Mm, I'm taking a global max, which is initially 0, taking a map of vector, because I'll just transform the vector and store it in a hash map. And then just make a mm, curve as like you can either make it true or false, but considering we will flip it on the basis of what we have, so I'm just checking if like uh this is not an that matrix of I 0 is 1, make it true, else false. So right now I'll just, what I said in the earlier phase, I'll just take XOR of it, because 1 1 will give me 0 and 0 1 give me 1. So if the square is 1, then it will always flip all the ones to 0, but if it's 0, then it will give me like 1 0 as 1, like it will give me every flip the like every bit to its complement bit. So matrix of I J is equal to, and I'll store matrix of I I'll store the maximum frequency. The time complexity of this like uh, solution is I'll log in because I'm traversing it once and it's using a map that will retain login operations every time it does, and the space complexity is login because, or it could be on if every matrix is different. Thank you for tuning in. Hope you see you tomorrow. Bye.